This lesson is for Advanced Algebra, Lesson 9.8 on natural logarithms. Natural logarithms are logs with base e. Why do we need those? There will be questions involving the PERT formula, where the exponent is unknown. In order to solve those, we need a log with a base e. So those types of logs are called natural logs, and we'll take a look at those in just a moment. Let's just quickly review the types of logs we've learned so far. A log without a base is called a common log. And those, even though the base isn't written, have a base 10. A reminder that the answer to a log problem is an exponent. So in this log problem here, the exponent is the y. So if we rewrote the common log problem listed here in exponential form, it would be 10 to the y equals x. So that's all a log problem is just a rearrangement of a power problem. The other types of logs that we've learned so far are logs with other bases. If there is a base listed, we just write whatever that base is to the power, to the answer, equals x. Now the new type that we're doing today is called a natural log. So know that we're not even using the word log anymore. There's an L there for log and then an N for natural log. Now I agree with you that it would make more sense that it said NL instead of LN, because natural log would be an N and then an L. But I think what they did here is they wanted it to be L for log, and then the type that we're doing is natural, so that's why it's LN. There is an LN button on your calculator, so let's take a look at where that is. If you do the control button and then the E to the power of button, you'll get an LN command, and we'll use that command here in just a moment. So a natural log problem is a base e raised to a power equaling x. So those are the type that we're going to be looking at today. And again, the reason we need those is to help us solve PERT problems. We're not going to deal with PERT at all today. We're just going to be learning and getting comfortable with natural log itself. So there's a bunch of practice problems we're going to do today, starting with natural log of 3. That one is a calculator question. You would be allowed to use a graphing calculator to calculate the natural log of 3. In fact, I'd like you to try that right now with me and round it to the 10th. So hopefully you already have natural log up on your calculator, and then just hit a 3 and then do a control enter to get an approximate answer. If we round that answer to the 10th, it would be 1.1. So we're going to say about 1.1. The other problems would be baby calc questions, questions that you would not be allowed to use a graphing calculator for. What I would recommend on all of these is that you fill in whatever's missing. In most of these, the thing that's missing is the exponent, because the thing that's missing is the answer. Now when you rewrite it in exponential form, since they're all natural log problems, they're all going to be base e. So base e to the unknown exponent has to equal a 1. Now this answer is not a natural log type question. This is just a general knowledge question. Whenever you raise any base to a power and get a 1, that power has to be a 0. That's something that students just simply need to memorize. The next one is, again, has a missing exponent. When we rewrite it in exponential form, it's a base e because it's a natural log. We don't know the exponent and we're trying to get to e to the 5th. Well, that one's pretty obvious. The power that they want us to find is staring us in the face. E to the 5th is what we're looking for, so the 5 is the exponent. On the next one, again, the exponent is missing. It's a natural log, so it's a base e. We're raising to the unknown power and we're trying to get to e. So if we're taking e and raising it to a power and getting e back, the power must have been a 1 to begin with. Our final one here is, if we rewrote it, base e because it's natural log, power is unknown, and we're trying to get to a -2. This type of question we have talked about before. You can't take a base, raise it to a power, and get a negative. The only way for that to happen is if the base was negative to begin with. So on this one you'll say no solution. We will come back and look at the word problem in just a minute. I want students to look at one more with me. Another type of question you might have to do related to natural logs is rewrite it in another form. Here is a natural log problem that they want us to rewrite in exponential form. So you have to remember that a natural log is a base e. And then just remember which number here is the power. Remember that the answer is the power. So if we take e to the 1.609 power, it should generate the number approximately 5. So then that would be your answer because you've rewritten the problem. I also want to look at a word problem with you. I took this right out of your textbook from page 631. According to this law, if you shine a 10 lumen light into a lake, the light intensity I at the depth of d feet under the water is given by this formula. Notice that the formula has a natural log in it. K is the measure of the light absorbance of the water. For a lake where the K is 34, at what depth is the light intensity 6 lumens? I'm guessing that people who do diving and search for things under the water do care about how intense their flashlight would be. If they need a brighter bulb, that would mean that they could see further under the water. Students do not need to memorize this formula. If they're doing problems like this, the formula will be given. All you have to concentrate on is finding the numbers, plugging them in the right location, and calculating correctly. So the first thing they give us is a value for K. Be careful there. The K value is indeed negative. So we're going to say negative 34 times the natural log of. We have two more variables here. They have to give us one of them. They give us a 6 lumens, and they tell us that that's an intensity, so that must be an I value. So then to find the depth, which is what they asked us to find, we would simply calculate. So grab your calculator, we're going to type that in. So I typed in negative 34 times the natural log of 6 over 10, or 6 divided by 10. Hit a control enter to get a decimal answer. We'd round to whatever they ask for. If we rounded to the 10th here, we'd say 17.4. If we rounded to the whole number, we'd say about 17. So the depth here is about, let's say 17, and it looks like we're measuring in feet. There's one other topic that I want students to look at today in the video, and that is about graphing. When you're graphing logs, the graph is always the reflection image of the original exponential curve. Exponential curves are always a base raised to an x power. If you reflect that exponential curve over the line y equals x, pictured here in blue, you'd get the logarithmic curve that is its inverse. So in this case, the natural log of x is the inverse of e to the x. The brown curve here that's a logarithmic curve comes from natural log. Notice that the logarithmic curve has no y-intercept. It never crosses the y-axis. And its domain is only positive values for x. So we're never going to the left of the y-axis. And the range, or the y-values, is all reals because we're going down forever and up forever. In a recent video, we graphed by hand and we used tables to do it. Today our graph here is simply a sketch of the two. So this is not necessarily drawn accurately, it's just a sketch of what you should be seeing when you type these in on the calculator.